One of the main ways hydrogen can be produced is by using solar energy to split water molecules into hydrogen and oxygen. This process, called water splitting, can happen through various technologies such as thermochemical, photoelectrochemical, and photobiological methods. For example, certain types of algae and bacteria use sunlight to break down water and generate hydrogen naturally under special conditions without oxygen, a process inspired by photosynthesis. Adding substances like magnesium hydroxide helps keep the environment right for these organisms to produce hydrogen efficiently. Besides biological methods, hydrogen can also be produced from waste materials like food industry wastewater, biomass, and other organic wastes. These waste-based processes use methods such as dark fermentation to convert organic materials into hydrogen. This not only helps produce clean energy, but also solves waste management problems at the same time. After hydrogen is produced, it needs to be stored safely and efficiently. Pressurized gaseous storage is one common method where hydrogen gas is compressed and stored under high pressure. This method is widely researched and developed to meet the growing energy needs while aiming to reduce costs and environmental impact. Governments and organizations worldwide, including the U.S. Department of Energy, are setting targets to reduce hydrogen production costs dramatically in the coming years, aiming to make it more accessible and affordable for widespread use. To make hydrogen a practical energy source, it is important to have a reliable system that can deliver hydrogen from where it is produced to the places where it will be used. These places could be factories, power plants, or even hydrogen fueling stations for vehicles. The hydrogen delivery system includes pipelines for transportation, facilities to turn hydrogen into liquid form, trucks that carry hydrogen, and storage sites. Right now, the technology for delivering hydrogen is quite developed. In the United States, for example, several companies already handle large amounts of hydrogen and deliver it commercially. However, as the demand for hydrogen grows all over the world, the existing delivery systems need to expand and improve. New technologies are also being developed to make delivery easier and more efficient. One example is using chemical carriers that can transport hydrogen in a denser form, allowing more hydrogen to be moved in less space. When transporting hydrogen in large amounts, it usually has to be compressed into gas form or cooled down to become liquid so it can be moved more easily. The location of hydrogen production plays a big role in overall costs. For example, producing hydrogen in a large, centralized plant can lower production costs, but might increase the cost of getting that hydrogen to customers due to transportation expenses. On the other hand, producing hydrogen in smaller, local facilities means production is more expensive, but the delivery costs are lower because the hydrogen doesn't have to travel as far. Delivering hydrogen from where it is produced to where it will be used is a critical step in building a successful hydrogen system. There are different ways to move hydrogen depending on how much is needed and how far it has to travel. In areas where hydrogen demand is high, such as industrial zones or regions with many hydrogen-powered vehicles, companies often build dedicated pipelines to carry hydrogen gas directly to users. These pipelines make delivery easier and more cost-effective over time. In places where the demand is lower or more spread out, hydrogen is usually transported by road. It can be moved in special trucks that carry hydrogen as a cold liquid or as a compressed gas in large tubes. These vehicles make it possible to deliver hydrogen even to remote or less developed areas where pipeline construction wouldn't make sense. Once the hydrogen arrives at its destination, certain facilities need to be in place for it to be used safely and efficiently. These include systems that compress the gas to the right pressure, tanks that can store it, and devices that check for impurities. For example, when hydrogen is used to fuel medium or heavy-duty vehicles, it's typically stored under high pressure anywhere from 350 to 750 bars and delivered at a fast rate, such as 10 kilograms per minute. This helps ensure vehicles can be refueled quickly, much like filling up a gas tank today. In the world of hydrogen energy, getting the gas from where it's made to where it's needed is a crucial step. There are two main ways that gaseous hydrogen is transported: by trucks and through pipelines. These methods are selected based on the distance it needs to travel and how much hydrogen is being moved. Hydrogen gas is usually produced at a relatively low pressure, around 20 to 30 bars. However, it can't be transported efficiently at that pressure. Before it's moved, the gas needs to be compressed to a much higher pressure, often 180 bars or more. This compression makes it easier to transport large amounts in a smaller space. When trucks are used, they carry hydrogen in special containers known as tube trailers. These trailers are equipped with long, high-pressure cylinders that store the compressed hydrogen. Tube trailers are ideal for delivering hydrogen over medium to long distances by road, especially to places that aren't connected by pipeline. Pipelines are another option, and they're generally used for transporting larger volumes over long distances. Pipelines are especially common in areas with a high demand for hydrogen, like near oil refineries. This is because hydrogen plays an important role in refining petroleum products, so it's efficient to have a steady supply delivered directly by pipeline. When hydrogen gas is produced, it usually comes out at low pressures around 20 to 30 bars. However, to move it from where it's produced to where it's needed, we have to compress it. This means we squeeze the gas into a smaller volume so it can be stored and transported more efficiently. There are a few main types of machines, called compressors, that are used for this job. One of the most common types is called a positive displacement compressor. These compressors work by trapping hydrogen gas in a space and then physically shrinking that space to increase the pressure. There are two main styles of these: reciprocating and rotary. Reciprocating compressors work a bit like a bicycle pump. They use a piston that moves back and forth to pressurize the hydrogen. This type is especially good when we need to reach very high pressures, and it's often used in hydrogen fueling stations or for storage. Rotary compressors work differently. Instead of moving back and forth, they use parts like gears, screws, or rollers that spin around. These compressors are great for moving hydrogen continuously, but because hydrogen is such a small and light molecule, it's tricky to keep it from leaking. Rotary systems need to be designed very carefully to seal tightly. Another type is the centrifugal compressor, which is used more for sending hydrogen through pipelines. This kind of compressor uses a spinning turbine to boost the pressure. It's really fast, much faster than compressors used for natural gas, and it handles a lot of hydrogen at once. That makes it perfect for large-scale pipeline systems. Besides these mechanical methods, there are newer, alternative ways to compress hydrogen. One method uses electrochemical reactions, where hydrogen is split and then recombined under pressure. This process uses a special membrane and electricity to do the work, and it's used in something called an electrochemical compressor. In this system, humid hydrogen enters at low pressure, and through a series of steps, it's compressed up to 70 megapascals MPa, ready for storage or use. Another approach involves metal hydrides. Certain metals can absorb hydrogen and form a compound when it's cool and under pressure. Later, when heat is added, the hydrogen is released again, but at a higher pressure. This method is also being explored as a safe and compact way to store hydrogen. Hydrogen can be transported through pipelines, much like natural gas. In the United States, there are roughly 1,600 miles of hydrogen pipelines currently in use. These pipelines are mostly found in areas with heavy hydrogen demand, such as oil refineries and chemical plants, especially near the Gulf Coast region. Using existing pipelines to move hydrogen is a cost-effective way to deliver large amounts of this gas. Building new pipelines, however, involves very high upfront costs, which makes expanding hydrogen pipeline networks challenging. Much of the recent research in this area focuses on solving technical problems related to hydrogen pipeline transport. Some key concerns include how hydrogen affects the steel used in pipelines, particularly causing brittleness in the metal and weld points, plus issues like hydrogen leaking out or passing through the pipeline material, a process called hydrogen diffusion. Researchers are also looking at ways to reduce costs and improve reliability, especially regarding how hydrogen is compressed before transport. One promising alternative to traditional steel pipelines is the use of fiber-reinforced polymer pipelines. These are made from composite materials rather than metal. They are considered better suited for distributing hydrogen to different sites because they are less prone to the problems steel faces with hydrogen. Additionally, fiber-reinforced pipelines are cheaper to install, about 20% less, because they require less welding during construction. A practical approach to quickly grow hydrogen delivery infrastructure involves using parts of the existing natural gas pipeline network. This is possible by slightly modifying pipelines to carry a blend of natural gas and hydrogen up to about 15% hydrogen mixed in. However, converting pipelines to carry pure hydrogen is much more complicated and expensive. Current research explores both adapting pipelines for mixed gases and developing new pipelines suitable for pure hydrogen. Another method for transporting hydrogen over longer distances is by using tube trailers. These are trucks equipped with long, high-pressure cylinders designed to carry compressed hydrogen gas. The gas is compressed to very high pressures, typically around 180 bars or more, and stored inside these tubes mounted on the trailers, hence the name tube trailer. In the US, regulations generally limit the pressure inside these trailers to 250 bars. Although exceptions exist allowing pressures up to 500 bars or slightly higher in some cases. Most tube trailers today are made from steel and can carry up to about 380 kilograms of hydrogen. The limitation on how much hydrogen they can carry mostly comes down to the weight and strength of the steel used. Recent advances aim to improve these trailers by creating storage tanks made from composite materials instead of steel. These composite tanks can carry much more hydrogen, between 550 and 900 kilograms per trailer, that are already being used in some countries to transport compressed natural gas. Hydrogen storage is very important because it can replace fossil fuels and help reduce carbon emissions. This makes hydrogen a big part of moving toward a cleaner and more sustainable future. Right now, hydrogen is stored in different ways depending on its form. It can be kept as a gas or as a liquid. When stored as a gas, hydrogen needs to be kept under very high pressure, usually between 350 and 700 bars, to fit enough of it into storage tanks. On the other hand, storing hydrogen as a liquid requires extremely low temperatures, known as cryogenic temperatures, to keep it in liquid form. Hydrogen can also be stored using solid materials. This happens through processes called adsorption or absorption, where hydrogen sticks to or is taken into the surface of certain materials. Because hydrogen is used in many applications like portable power devices, stationary power plants, and transportation, how we store it efficiently is crucial. Hydrogen has the highest energy per mass compared to other fuels, meaning it packs a lot of energy in a small weight. But its density at normal temperatures is low, so the energy per volume is smaller. This means we need advanced ways to store hydrogen safely and compactly to use it widely. There are two main types of hydrogen storage: physical storage and material-based storage. Physical storage includes storing hydrogen as compressed gas, as a very cold compressed gas cryogenic, or as a liquid. Material-based storage involves storing hydrogen inside different materials, which include adsorbents, liquid organic carriers, metal hydrides, complex hydrides, and chemical hydrogen storage. Current research is especially focused on metal hydrides, chemical storage methods, and special materials called sorbents that can hold hydrogen well. Storing hydrogen as a gas means keeping it under high pressure to fit enough gas into a container. Typically, this involves pressures ranging from about 35 to 79 megapascals MPa, which is very high. Often, this storage happens at cooler temperatures to help keep the gas dense and manageable. One drawback of this method is that around 11% to 12% of the hydrogen can be lost or wasted during storage, which is an important factor to consider. For storing hydrogen gas commercially, containers made of steel or aluminum are commonly used. However, these metal containers sometimes experience small leaks because hydrogen molecules are very light and can escape through tiny imperfections. To address this issue, vessels made from carbon fiber reinforced materials are becoming more popular. These materials are stronger and better at preventing leaks compared to steel or aluminum, making them more suitable for safely storing hydrogen gas. When it comes to storing very large amounts of hydrogen for longer periods, certain geological formations like large underground caves or salt caverns are ideal. These natural spaces can hold hydrogen securely and prevent it from leaking, even under very high-pressure conditions. This makes geological storage a promising option for utility-scale hydrogen storage. Storing hydrogen in liquid form means cooling it down to extremely low temperatures, around 20 Kelvin, which is close to minus 253 degrees Celsius. This very cold storage is called cryogenic storage. One big advantage of storing hydrogen this way is that it takes up much less space compared to storing it as a gas. Because of this, the energy packed into each liter of liquid hydrogen is much higher. In fact, the energy density, meaning the amount of energy stored in a given volume, increases from about 2.5 megajoules per liter mJ, L in gaseous form, to around 8.0 mJ, L when stored as a liquid. This means you can store more energy in a smaller space, which is helpful for applications that need compact storage. At the boiling point of hydrogen, which is about 20 Kelvin, its energy density is roughly 1.8 times greater than hydrogen compressed at very high pressure, around 70 megapascals. This makes liquid hydrogen storage a more efficient way to hold energy in terms of volume. However, cryogenic storage also comes with some challenges. It requires a lot of energy to cool hydrogen down to such low temperatures and keep it cold. This high energy need can increase the overall cost and complexity of the storage system. Despite these drawbacks, liquid hydrogen storage remains an important option for storing large amounts of hydrogen, especially when space is limited. Storing hydrogen in solid form, especially using metal hydrides, is an interesting but challenging method. It is not usually suitable for storing very large amounts of hydrogen because it tends to be more expensive than storing hydrogen as a liquid or gas. Additionally, this type of storage requires a lot of space and complex systems, which makes it harder to use on a big scale. Safety is also a major concern when using metal hydrides for hydrogen storage. Despite these challenges, metal hydrides are useful in situations where it is important to have a material that can absorb and release hydrogen repeatedly and reliably. Hydrogen can also be physically absorbed by materials like fullerenes, carbon nanotubes, metal organic frameworks, and activated carbon. These materials are good because they can hold hydrogen and release it again easily, which is called reversibility. However, their ability to store hydrogen at room temperature is quite limited. That means they usually need to be kept at low temperatures to store a useful amount of hydrogen. Metal hydride storage is considered a promising and advanced technology, especially because of its safety advantages. One key benefit is that it works well with low-pressure equipment, making it simpler and safer to manage compared to very high-pressure tanks. The process of storing hydrogen with metal hydrides is also highly reversible, meaning hydrogen can be absorbed and released many times without damaging the storage material. These metal hydrides are used not just for storing hydrogen, but also in other applications such as sensors, switch mirrors, and batteries. One interesting aspect is how hydrogen quickly interacts with the surface of metal hydrides. However, if the particles on the surface clump together too much, it can make the surface less stable. To fix this, researchers have developed composite materials where nanoparticles are coated with magnesium oxide. This coating helps prevent the particles from clumping and improves both thermal and mechanical stability during hydrogen storage and release. Another effective type of metal hydride is called intermetallic hydrides, especially those made from rare earth metals combined with nickel or cobalt. These hydrides can absorb hydrogen very well and show excellent reversible storage behavior. The absorption process itself releases heat, which means the storage tanks need to be cooled efficiently to keep everything working properly. Hydrogen can be stored by interacting with tiny, porous materials called microporous materials. These materials have very small pores and a large surface area where hydrogen molecules can attach. The way hydrogen sticks to these surfaces is through weak forces known as van der Waals forces. These forces are quite gentle, meaning hydrogen doesn't form strong chemical bonds with the material, just a thin layer, or monolayer, of hydrogen molecules attaches to the surface. The energy needed for hydrogen to stick to these microporous surfaces is very low, which makes this storage method different from chemical storage where strong bonds are formed. Because of this, hydrogen can easily attach and detach from the surface, making it a reversible process. The amount of hydrogen that can be stored this way mainly depends on how much surface area the microporous material has. A material with a larger surface area will hold more hydrogen. Other factors, such as the size of the pores and how evenly they are distributed, also affect how much hydrogen the material can store. Understanding these details helps in developing better materials for storing hydrogen efficiently. When storing hydrogen gas at high pressure, the density of hydrogen increases as the pressure goes up. This means more hydrogen can be packed into a smaller space, which is very useful for storage and transportation. High-pressure gaseous hydrogen (HPGH) to storage works by compressing the hydrogen to pressures typically between 35 and 71 megapascals MPa. This pressure range is considered ideal for systems that store hydrogen onboard vehicles, balancing factors like how far a vehicle can drive, the energy needed to compress the gas, costs to build infrastructure, and other important considerations. At hydrogen refueling stations, hydrogen is usually kept at pressures between 40 and 75 megapascals. This high pressure allows for quick refueling because hydrogen naturally moves from areas of higher pressure the station to lower pressure the vehicle tanks, making the refueling process efficient and fast. The storage vessel that holds this high-pressure hydrogen is one of the most important parts of the whole system. These vessels come in different types depending on how the hydrogen will be used. There are stationary vessels used for fixed storage locations, vessels designed specifically for vehicles, and larger vessels meant for transporting bulk hydrogen over longer distances. Stationary high-pressure hydrogen storage vessels are commonly used at hydrogen refueling stations and other places where large amounts of hydrogen need to be stored at a lower cost. These storage systems hold hydrogen gas at very high pressures and are designed to safely store large volumes of hydrogen for use over time. Currently, two main types of stationary storage vessels are used: seamless vessels and multifunctional layered vessels. Seamless hydrogen storage vessels are made from high-strength steel tubes without any seams or welds. These tubes are manufactured following strict safety codes to ensure they can handle high pressure safely. To store a large volume of hydrogen, many of these vessels are connected together with pipes and valves to form a large system. However, these seamless vessels have size limits because there are restrictions on how large and thick the steel tubes can be made. The maximum pressure these vessels can safely handle is around 65 megapascals MPa, with a typical volume of about 0.41 cubic meters per vessel. Because of these limits, refueling stations need many vessels assembled to hold enough hydrogen. To increase the pressure limit and volume, steel is used to strengthen the vessels, but this comes with a problem. When steel is exposed to high-pressure hydrogen, it can suffer from a phenomenon called hydrogen embrittlement. This makes the steel brittle and more likely to crack, especially as the pressure increases, which is a serious safety concern. To address these challenges, a different type of vessel called the flat steel ribbon wound cylinder (FS or WC) was developed. This multifunctional, layered vessel is made up of multiple shells, including an inner shell, a layered middle shell, and an outer protective shell. Because of this layered design, FS or WC vessels don't have the size limitations of seamless vessels. This means they can be made longer and thicker, allowing them to safely store hydrogen at much higher pressures. Vehicles powered by hydrogen need a special kind of storage vessel to hold hydrogen safely and efficiently onboard. The goal is to store enough hydrogen so the vehicle can travel a good distance without refueling too often. Back in 2003, the U.S. Department of Energy suggested that an onboard hydrogen storage system should hold at least 6% of its weight in hydrogen and have a density of about 60 kilograms of hydrogen per cubic meter. This was said to enable a driving range of around 500 kilometers with just one fill-up. Since then, many hydrogen-powered vehicles have been tested and the requirements for storage systems have been updated. By 2009, the minimum needed was adjusted to hold at least 5.5% hydrogen by weight and have a volumetric density of 40 kilograms per cubic meter. To meet these targets, two main types of storage vessels are commonly used. Type IV and Type V. Type IV vessels are made with a metal liner wrapped completely with strong carbon fibers. Type V vessels are similar but use a non-metallic liner instead. The liners are typically made from high-density polyethylene, a tough plastic, wrapped tightly with carbon fiber to provide strength while keeping the vessel lightweight. There have been advances in the design and manufacturing of these vessels. For example, in 2000, a lightweight Type IV vessel called TruShield was made, which could operate safely at 35 megapascals MPa of pressure. Just 2 years later, in 2002, another Type IV vessel called Tough Shell was developed to handle pressures up to 70 MPa. Recently, using advanced quantum technology, it has become possible to make Type IV vessels that store about 5 kilograms of hydrogen at 70 megapascals pressure, a volume of around 129 liters. Type IV vessels use high-performance composite materials, making them both strong and light, which is very important for vehicles. However, the plastic liners need to be very durable and compatible with hydrogen over the entire life of the vessel. Researchers from groups like the Commission for Atomic Energy in France and Toyota Motors are actively working to develop better liners using materials like polyamide and polyurethane to improve performance and safety. When it comes to moving large amounts of hydrogen from where it is produced to where it will be used or to refueling stations, special storage vessels are needed. These vessels are designed to carry hydrogen gas at very high pressure, usually between 16 and 20 megapascals. The vessels used for this purpose are seamless and built to handle these high pressures safely. Each trip typically carries no more than about 280 kilograms of hydrogen. This method of transport is quite common for delivering hydrogen over long distances, especially when large volumes are involved. In addition to transporting compressed hydrogen gas, hydrogen can also be transported in its liquid form, which is cryogenic hydrogen. Moving cryogenic hydrogen by rail is often more cost-effective compared to road transport using tube trailers. However, in reality, very little hydrogen is transported by rail. This is mainly because there are challenges such as poor scheduling and insufficient railcar capacity to handle cryogenic hydrogen safely and efficiently. Storing hydrogen safely and efficiently is a big challenge, both for portable uses like vehicles and for stationary setups such as power plants. It is also difficult when transporting hydrogen from one place to another. Most current storage systems need large tanks to hold hydrogen gas because hydrogen is very light and takes up a lot of space. For example, fuel cell vehicles need enough hydrogen stored on board to drive over 300 miles, but making that storage compact and safe is not easy. Hydrogen is a very light and highly flammable gas, which makes it tricky to handle. There are several ways to store it, such as compressing it into high-pressure tanks, cooling it into a liquid form at very low temperatures, or storing it in solid materials. Each method has its own problems. Compressed gas storage requires strong and heavy tanks that can handle very high pressure, which makes them costly and bulky. Liquid hydrogen storage demands extremely cold temperatures that are difficult and expensive to maintain. Solid-state storage, which involves storing hydrogen inside materials, is still being developed and isn't yet widely used commercially. Despite these difficulties, many scientists and companies are working hard to find better ways to store hydrogen. Some are creating new materials that can hold hydrogen safely at lower pressures, which would reduce the need for heavy tanks. Others are developing catalysts that help produce and store hydrogen more efficiently. There is also research into using substances called hydrogen carriers, which can transport hydrogen more easily without the need for high pressure or extreme cold. These advances could make hydrogen a practical and widely accessible energy source in the near future, helping reduce reliance on fossil fuels and lower carbon emissions.